light is made up of both electrical and magnetic fields. This is great because we home in on either one or both of those things to see them or detect them. On the high energy end, we use detectors. On the low energy end, we use antennas. And it can be called anything you want in between. So detectors or sensors, antennas, eyeballs, telescopes, they all become really synonymous in the big picture of things. All right? All right. Some of that light from the outer, from extraterrestrial, not all of that light gets through to our surface. As you can see from this picture over here, that the stuff that makes it to the surface are the visible, okay, and the radio, some infrared, some microwave, but none of the high energy stuff like the UV, the X-rays, and gamma rays. And you can say, thank you for that. As it turns out, if we didn't have an atmosphere or we didn't have a magnetic field, we would be in deep poo-poo with these things over here, you see, because they would interact with us and we could become mutants and make a whole new series of science fiction movies or something. So, real briefly, I don't want to spend any time on this, just to let you know how a radio wave's produced. It's really simple. I'm just going to tell you and then I'm going to cut to the chase. Basically, it's this. When you have a bunch of ions out there, electrons, just charged particles, and they move, if they change direction, they're going to emit light of some kind, usually radio, but it could be other, it could be UV, it could be anything, depending on how fast they're moving, how fast they're changing direction, okay? Accelerated charges will emit radiation. Accelerated means if there's a change in velocity, not just the magnitude, but direction, then you can have emission. That's one of the main ways that we produce radio waves. The sun is a hot ball of gas. It's ionized. Yeah, it's only 6,000 degrees on the outside, but inside is 15 million or more, okay? So the gas is ionized for the most part. And so you have a bunch of electrons and protons just whizzing by, and that's generating a bunch of radiation, radio waves. You can listen to them, and we will. When I say listen, you'll see what I mean in a minute. You can detect them pretty easily. But there are other ways. Sometimes if the particle is whipped around a magnetic field, remember, you may or may not know, a magnetic field does no work, or a particle does no work against a magnetic field, or vice versa, okay? An electrical field is a different story, but a magnetic field, it just deflects, it just changes the direction, it doesn't do any work. So, but the fact that you have a change in direction as the electrons gyrate around the magnetic field line, they too can generate radiation. But here it's going to be different. And depending on the speed of the electron, if it's like flying like a bat out of hell, so to speak, relativistically close to the speed of light, then the radiation pattern is going to be very different. And it'll be, and those differences help us actually detect them. Okay, and that's called synchrotron radiation. And finally, the discrete sources is this, and I'll just go to the discrete source to show you the most important one, and that's this one here. It's called a hyperfine transition. Now, you remember that when it comes to atomic particles and such, small entities, the energy levels that are available to the particles are no longer continuous as they are in the big picture, things like us moving around or cars, but rather they're discrete or quantized. All right, so that the energy gets very like there are ladders of energies. With each rung is where they can reside, but not in between. Well, in one example, we have the hydrogen atom, which is the most typical element in the universe because it's the simplest. One hydrogen, one proton, and one electron all around it. Now, the proton can spin on its own, and the electron can spin on its own. When they both spin in the same direction, that's a slightly higher energy than if one is spinning in one direction and the other one's spinning in the other. Doesn't matter which one's which. That difference in energy happens to be, if you calculate it, right in the radio range. This is called 1.4 gigahertz. That's megahertz is a million, gigahertz is a billion. Okay, so it's 10 to the 9 hertz. And sometimes we talk about light in terms of wavelength. Either we can talk about frequency or we can talk about wavelength. That's, in other words, a wave would be meters. That's what, about 8 inches or something, right? Something like that. 2.5 centimeters to an inch. All right, so this is the thing that we can zoom in on because the universe is made of so much of the stuff, of hydrogen. So this is, we can take to our advantage. All right, now, here is a picture of the sky from Greenbank, West Virginia, but it's not your typical picture. This picture is not invisible light. This picture is in radio light. Ooh. Well, you mean these little specks here aren't stars? No, they're galaxies. That's really wild. And you'll see that there's this gray, it's not a black sky, but a grayish sky. Why? Anybody? Interaction's fine. Anybody want to guess why the sky in the radio is not black, but grayish? Any guesses? Any guesses?
Radio waves open vacuum.
Good guess, but no. There's another answer. The what?
It doesn't recognize the light.
The what?
It doesn't recognize the light.
No.
No.
The night sky is black to the visual, to the eye, right? You think, sorry, it looks dark. It looks real dark, right? Why? Because the light from the stars from the beginning hasn't reached us yet. And it was Edgar Allan Poe, by the way, who came up with that piece of trivia, if you wish. That insight into physics came from a poet. Edgar Allan Poe, yeah, the same guy who wrote the Pendulum and all that. That guy. Because he was interested in astronomy too. The light hadn't gotten to us yet. So that's a hint. What happened in the beginning? Well, as far as our understanding of models go, there was something we call the Big Bang. And the cosmic microwave background radiation permeates the entire universe. That's about 3 degrees Kelvin. That's what this is. This gray is all the cosmic background radiation that's filling the sky. That's why it isn't black. It's filled with microwaves. That's why. Now, what I want to do, hold on. What I want to do is I want to exit out of this slide. I want to show you a picture. Hold on, don't panic. I want to show you a picture of, here's the same picture again. Forgive me for, hold on, play from the current slide. Here's the one you just saw. But I just happen to have the same picture in another program. Why? But look what happened. This is a picture, an optical picture by the Hubble Space Telescope of something we call Cassiopeia A. It's in Cassiopeia constellation with big W's in the sky. All right. This is a Hubble telescope image, and what do you see? You see a bunch of gas that's being illuminated by ultraviolet light, and it glows. And you see, and this is an actual color. This is real. This is not colorized. This is the way it really looks. Now you have no idea how big this guy is, but this guy can be studied in all kinds of light. I mentioned Cassiopeia because it's one of the most obviously strong radio signals out there. Here's a picture. You superimpose various wavelengths of light: visible, infrared, X-ray, and together all the astronomies work together to shed some light on what's going on. Now, what is this Cassiopeia A? What is it? It is the remnant of a supernova explosion. And a supernova, you might remember, is when a big star, a star at least 8 times more massive than our own star, which is a yellow dwarf, all right, will end its life. Okay, and it ends its life by a cataclysmic self-destruction event called a supernova. All right, this is what's left over of the supernova. What's in the middle of the supernova, or depending again on the size of the star, either you're stuck with a neutron star or a black hole. If it's massive enough, the star, you'll end up with a black hole. So here we have something called a supernova remnant. that is very pronounced in the radio. Let me show you a picture of it in the radio alone. In fact, using different radio frequencies. Now, most of the stuff is not available. The 8 gigahertz stuff is probably not available to the amateur. The 5 gigahertz, kind of, sort of, because we can look at 4 gigahertz with your regular C-band TV. And 1.4 gigahertz we just talked about. So this is a composite in the radio, and it shows some pretty interesting stuff. Now, I forgot that doesn't matter. I just wanted to give you, now this is obviously a false color image because you can't see in the radio. But look, I want to show you something really wild here. This is a false color image of Cassiopeia A superimposed on an optical image of the sky at, I want to say Greenback, but I'm not positive. It probably is. You see NRAL. So, notice how big it is. As a target, I mean, what you see when you look at Cassiopeia, you see a little W. That's not huge. This is huge. The radio image is pretty big, and this is one reason why it's easy to detect this guy. Now, just hot off this press, this is why I stuck it in here, just hot off the press, like yesterday. That's how hot this information I'm going to give you is. Cass A, with an X-ray telescope called Herschel, did I spell it right? I hope I did. Herschel X-ray telescope, a fairly newly commissioned X-ray telescope, took this picture of X-rays coming off one of the elements that are produced in the supernova explosion called titanium-44, that specific isotope, and then zooming in on those X-rays. Now, what does this all mean? What's it all mean is something, it's shedding some light on how supernovas die. This is the problem, it's making computer models, and you need supercomputers to do it, like at Oak Ridge, some of the fastest, probably the fastest computers in the world are in Oak Ridge, Tennessee, not too far from where I live. These supercomputers are able to make these complex calculations. And it turns out that when you're trying to reproduce the conditions that make a star supernova, a lot of them fail. I mean, we couldn't make it happen. And what's going on? Well, it turns out that there's the star starts to collapse on itself. The shock wave is produced as a rebound, and that shock wave is what tears the star apart. The only trouble is that most of the computer models are showing that the shock wave stalls out. Okay, so scientists believe very much in these models were accurate. So what they thought what might happen is that some jets re-energize the shock and allow the star to go supernova. And that's what happens in real life. And that was thought before February 19th of this year. Now, it's just published in Nature as of yesterday. The idea, because of this X-ray data, this is the X-ray image, the X-ray image of titanium-44. Notice how it's all clustered in the middle. It was previously thought that that would be all distributed throughout the whole supernova, but it's not. It's listed in the middle. So it suggests that what's happening to this massive star before it finally goes is that there's this sloshing. You just visualize a glass of water, and that you just start moving in your hand and how it sloshes, and that sloshing is what re-energizes the shock and lets it go. So this is really exciting. So did you notice that's not radio astronomy? But radio astronomers work in concert with all other astronomers, and that's what I want you to come away with. Okay, so let me escape from. Okay, well, while I'm here, let me show you a picture of this. The center of our galaxy. You know, when you on a clear night over here, you can see that band of what some people think are clouds. It's just a Milky Way. And if you have, I don't know how, it's probably pretty great over here, I imagine, on a clear night. You can see the band. All right, so it's tilted at a pretty steep angle, which means that it really isn't tilted. We are tilted. Our solar system orbit is tilted like 60-some degrees to it, right? So when we look, it looks like it's arcing the sky. But so if you were to look in the south on a clear night, you would see the constellation Sagittarius. And that's the direction you would look in if you wanted to peer into the center of our galaxy, which is 26,000 miles, no, a little farther than that, 25,000 light years away from where we are. With a light year, almost 6 trillion miles, 5.85, almost 6 trillion miles for 1 light year. There's 26,000 light years to the center of our galaxy. Now you can't see the center because there's gas and dust. You can't see it with visible light, but you can see it with radial light. And this bright blue, oh, it's lovely. Not blue, there's a hot spot there. This is the center of our galaxy in the radio. And radio astronomers rename things. So instead of calling it, well, they like to call it Sagittarius A. All right, this is a radio target. And you'll hear words like Taurus A. Well, that's another word for the Crab Nebula. Back when Taurus A was discovered, we didn't know that that was the same thing as the Crab Nebula. Okay, so or M1 is an Messier object. You might be familiar with that one better. Okay, so the point is that radio allows us to look inside of these things. And I'm going to escape out of this and go back to my regular presentation. And slideshow, current slide. Okay, this is where we were, and now that I got you all excited about radio astronomy, what can we as amateurs do? Well, we haven't got a multi-million-dollar budget, but we have resourcefulness, and we have radio waves that do come through the atmosphere, and we can learn an awful lot. We can have a lot of fun. You know, it's like this. Look, you look at a Hubble Space Telescope picture, and you ooh and you ah, and sometimes you wonder, I ain't never going to see anything like that through a telescope, a 4-inch telescope, or a 20-inch telescope, or a 200-inch Mount Palomar telescope. It ain't going to happen. You're not going to see those pictures that Hubble takes. But still, every time, I guarantee you, you go out tonight and you look through the telescope and you look at Jupiter, or you look at the double-double, or you look at a carbon star, you find some object that may not be anywhere near as good as Hubble can do, but you're still on. It's still fun. It's still exciting because you are part of that discovery. Well, the same thing with the radio astronomy for amateurs. It's not like you need to be a multi-million-dollar facility. You can still detect. Like, admittedly, they're not pictures. You have to maybe be happy with static noise or wiggle lines on the oscilloscope or something. But you know, hey, there was this chick. Well, no, she wasn't a chick. She was a lady. Her name was, what was her name? Oh Lord, don't tell me. I know her name. I know her boss's name, Anthony Hewitt. Her name was Burnett. It's her middle name. What's her last name? I forgot. But she was a graduate student in England back in, I guess it was just at the eve of astronomy becoming recognized as a science for a Nobel Prize. In fact, it wasn't astronomy. I still considered it a bastard child, so to speak, because it was just observational. But it was astrophysics, on the other hand, was coming into vogue. And the first Nobel Prize in astrophysics was awarded to Hewitt, not his graduate student, this lady who should have gotten it. His name escapes me right now. But she thought she discovered little green men, you see? Because of these, what turns out to be pulsars. She discovered pulsars, which are these rotating neutron stars that's sending these radio waves very regularly at us. And but anyway,
Jocelyn Bell.
yes, the one. That's the one. Burnett Bell. That's the one. Thank you. Jocelyn had then later gone into gamma ray spectroscopy, and she claims she never was bitter about all of that. But there's a clear case of graduate students getting dumped on, and not to mention females, too. That was a rough time. This was what, 1967, I think. So you see, pulsars are so fairly. I mean, you're all born then. I don't think. That's a pretty recent discovery. More than 75% of what we know about the universe is because of radio waves. Okay, I'm going to move on. So what can we as amateurs do? We can do a lot. You recognize this picture over here? This looks like a 10-foot dish. I don't know, it could be anywhere from 7 to 12, I guess. I got one in my backyard. That's how I used to watch TV, with a C-band satellite dish, you see. Then they migrated everything off the C-band onto these digital dishes that always burp when it rains, So I didn't renew. So I don't have TV. What do? I guess I watch movies on DVD. Or think about physics or write poetry. Yes, that's what I do. But I do miss TV, not too much, but I miss it. But here's a radio telescope in the making. That is to say, these satellite dishes only have to be changed a little bit. And yes, they are big enough to detect some pretty neat stuff. For example, the unit of energy, or power, the brightness, how bright an object is called a Jansky. Now the Jansky is really small, but we can detect easily anything at 100 Janskys. Now the professional folks like NRAO and the rest of them, they are looking down to milli Jansky, thousands of 1,000th of a Jansky. That's how sensitive their telescopes are. But you know, our backyard stuff, look at Cassiopeia. I mean, you know, I know, just on a relative scale, all of these things are fairly strong targets, and they're all easily and more. There's more than these that you can see with your detect with your 10-foot dish at home. Okay, that's kind of cool. I think it's cool. See how strong Cassiopeia is? You saw how big it was in the sky, right? No surprise, right? All right. So here's a picture of our galaxy as in what you call right ascension declination. Let me explain. You know, when you look on a map, you have latitude and longitude to locate things on the map. Well, picture that same, but now the map is kind of like you're looking at, you're superimposing this map in the sky, all right? And so depending on how high up you go in the sky, we call that right ascension. It's just like, very much like latitude, right? No, I'm sorry. Right, this is how it declined. Okay, the declination is like latitude, right? But right ascension are these lines of longitude. You see, so I can go right ascension, which also tells me the time, or I can go the declination to pinpoint an object in the sky. Well, this is what this map is, and what this is a sketch of energy. It's kind of like a map of those, you know, a topographical map, which shows you the relief, the mountains and the valleys, okay, the circles, the contours correspond to elevation. Well, think of these as like elevations, not in terrain, but in energy, okay, in radio energy in particular. So you see over here, where it's pretty intense radio source, this is the middle of our galaxy. This is what you can't see with your eyeballs, but you can with an even modest radio telescope. And then there's some other objects that are pretty cool, all right? This is a picture which shows you a whole bunch of stuff, some of which you can see, some of which you can't see. But you'll notice the frequency in megahertz. This is high frequency. Here's 1,000 megahertz. This is 1 gigahertz, right? That's 1 gigahertz. So 1.4 gigahertz, which is where we would normally like to see that discrete thing, which then they'll be about here, all right? So notice that some of these things, like the Orion Nebula, the lines get bigger as the frequency increases. Other things, like the active sun and the higher frequency, the slope of the line in the other direction. Okay, this has to do with that thermal and non-thermal stuff I was telling you about earlier. But you can identify. But notice this scale is logarithmic. You know, you don't have to memorize these numbers. It's sufficient to say that if we're like, these are Janskys, all right? So remember, this is our limit of detections about here. So anything above that point, you probably can see, all right? And we're going to concentrate on the frequencies that are around 20 megahertz, all the way up to gigahertz or so. Okay, so that's what we're interested in. You can see a lot of those things pointed out are up there. All right, let me move on. There's that famous picture. Oh, I didn't. Okay, hold on, don't panic. But I think it's just this picture. Okay, it's just this picture. Here's that Sagittarius, the middle of our galaxy picture. False color images. Okay, false color images. I want to show you something that I did because, you know, how exciting can it be to look at a strip of chart paper with a couple of peaks? This is actually two signals, the red one and the blue one, they're telling the same thing. And what it is I'm sitting at this 40-foot radio telescope that we can use for educational purposes at the Green Bank. Okay, 40-foot dish is it's a good-sized dish, bigger than most of us are going to have in our backyard. All right, and so it's just sitting there, and the sky rotates into view. Now, there is one thing I can do with this dish that I can't do with some other ones, and that is I have motors on the telescope, and I can make a telescope go up and down in declination, and I can't really move it in right ascension. I have to wait for the sky to drift into place, but while it's drifting into place, I have the ability of running rapidly the declination motor up and down, so I can do a quick vertical swipe as it's slowly passing by. And that's what I did here. So what I'm trying to do is to get the detection of a piece of the middle of the Milky Way, a piece of the middle of the center, okay, by running these strips of signals and then putting it all together in a three-dimensional plotting program. And this is what I got. I got a piece. This is a three-dimensional image. Now this is kind of cool. I mean, I don't know. I get excited about it. It was fun to do. But anyway, that's a piece of radio astronomy for the amateur, if you wish. You could do a version of that as well with your own. If you have a motor that can move fast enough, you can do it. All right. So what can the amateur do in general? A variety of programs. There's a variety of things, and I'm just going to throw a list out here. But there's more than this, and we're not going to discuss all of this. I'm going to focus in on a couple, three of them, so that this college might have an interest in pursuing, because they're not expensive, and they're fun to build, and they're gratifying to enjoy. The first thing is at the high frequency end, which is low frequencies in 20 megahertz. I may not have mentioned it to you, but you have to be above 15 megahertz before the radio waves penetrate our ionosphere. Okay, so any stuff outside, any radio sources out there have to be at least 15 megahertz for the most part for it to get through our ionosphere. Otherwise, we'll just bounce off our ionosphere like a mirror. All right. So 20 megahertz, we should see. What's at 20 megahertz? Our sun, Jupiter, and acoustic and stuff like that. So you can build. Now, it's not going to be a dish. At 20 megahertz, you don't have to build a parabolic dish. All you have to do is string up a couple of wires, make like we'll call a dipole or half dipole antenna. I'll show you a picture. All right, and these are pretty cheap kits. You can buy them turnkey, I think, for a few $100s, but you can build it yourself for. I don't think it's going to cost you more than a couple $100 to total cost. I mean, it's really getting expensive. All right. Other things you can do, which I'm not going to talk about except just to mention it. FM scattered meteors when they travel across the sky. Remember, especially the ones that you can see, the bolides. They leave that beautiful green trail from the ionized, excited oxygen atoms, right? All right. That ionized trail acts as a mirror in itself. So FM radio waves over the horizon, when they travel up, can bounce off the meteor trail to your receptor over here. So all you have to do is locate it over to your horizon, like for example, a couple 100 miles or less, over your horizon, FM radio station that you tuned into, and then the meteors, and you should be able to pick up a station that you normally wouldn't be able to pick up because of that. And you just record the blips and the ticks and whatever, and you can And that's a lot of fun. The Canadians are big into this. They got it down to a real art science. Again, very inexpensive and fun to do. There's something called sudden ionospheric disturbance. I'm going to talk about this, but in a nutshell, it's this. We have this ionosphere that I mentioned. It's about, gosh, what is it? 80 kilometers is where it starts. All right, 1.6 kilometers per mile. So it's up pretty far, way above our atmosphere. But that's where the ion, because of the sun and its energy, ionizes the molecules. Okay, it's a little rare, but I mean sparing. It's not dense out there, but nevertheless, there are ions out there. These ions, it's called the ionosphere, and it stretches all the way up to maybe 1,000 kilometers. Okay, so it's pretty big before you get into the deep outer space. This is what does this. So how is that important to us? Well, think about this. Up here in Colorado, I think just north of us, I think it's called Coulter. Is that right? Coulter? Does that ring a bell? Coulter. What's that place beginning with C? It's up north. Yeah, I can't think of it. It's a military facility, mostly for submarine communications. We're talking about emissions. We're talking about huge antennas that string between one mountain peak and another, so they're long, and they transmit strong signals, like 1,000 kilowatts or something. Maybe not that much. Yeah, maybe 1,000 kilowatts.
So not NORAD?
Well, it's like NORAD, but it's not NORAD. It's around 25 kilohertz. So frequencies that are low compared to, they're called very low, VLF, very low frequency. 25,000 cycles per second is low. We're talking about megahertz and gigahertz, and here's kilohertz. Well, if there was something out there in space generating 25 kilohertz, it wouldn't get through, it would bounce off. But stuff that's generated here on Earth, terrestrial VLF, it goes up to the ionosphere, bounces off the ionosphere, and is detected hundreds of miles away, 800 miles away. All right. Well, check this out. If you do anything to the ionosphere, you're going to affect how that VLF wave travels. So if there's a sudden disturbance in the ionosphere because the sun had a bad hair day and throws these coronal mass ejections at us and causes the tremendous flare that just suddenly ionizes our atmosphere. For a moment, our ionosphere becomes a better mirror, okay? And so the signal that you're receiving will be suddenly enhanced, okay? So you can use terrestrial radio astronomy, so that you can use terrestrial radio emission to tell you something about radio astronomical phenomena, like what's going on with our sun. But not just with our sun, it could be a galaxy or a magnetar that has a sudden burst of gamma rays that come this way. SGR 1860 was such a thing that lasted 8 minutes instead of just a few seconds, and 50,000 light years away produced a very strong detection with amateur equipment on this planet. That's scary. A SID thing, this is what we affectionately call, also very inexpensive. We're looking at $100 plus the materials to build a loop antenna, another 30, 40 bucks. You're in like flame. Software's out there, it's fun. And these are sounds that are, well, what do you mean radio? There's radio astronomy has nothing to do with listening, but what we do that's really cool in radio astronomy is that we'll take an electromagnetic wave frequency and do its direct conversion to an acoustic frequency, all right? And maybe down converted so that you can hear it, because you're not going to hear 20 megahertz, you know, but you can hear a few kilohertz, you know. So you down convert the frequency, so you make an audible record. You know, like you have false color. This is like false sound, if you wish. You have an audible record of what's going on. So you can see or hear both what some interesting things are going on in our magnetosphere and the outer fringes of our atmosphere, ionosphere, when we get bombarded with a bunch of solar wind, which is a bunch of charged particles, mostly protons. They bump into our magnetic field lines, it shakes things up. Some of these ions get caught in our magnetic field and they spiral and move and they change speeds and they're emitting different frequencies, and some of them go, they'll make what's called whistlers, or sometimes they'll just chirp and tweak, and they'll make all these noises when you convert them, and that's called natural radio. And it can be pretty interestingly hypnotic. And there's other stuff, but let me go ahead and just show you some pictures now before this thing goes to sleep again. This radio choke receiver, which is available, like I said, either I recommend that you all buy it and put it together yourself. Because you solder, there's a lot of fun to be learned from soldering. And if you have an engineering program here, they might be able to help you solder it, and you can have a first light party, and then listen to the sun and Jupiter. It's really cool. Here's the sun. It emits a whole lot of stuff. Fireball. Okay. What is this? Oh, forget that. There's Jupiter and its weird magnetic field, and what's traveling in this donut, this Taurus, is its moon Io. Now, what's so cool about Io is that it's the most volcanically active object in our solar system, and it makes us look pretty bad. I mean, there's a lot of volcanoes going on, and those volcanoes, Io doesn't have much of an atmosphere. It's got probably more of an ionosphere than an atmosphere. It's a little moon, but it ejects a bunch of junk out there, like sulfur atoms and such, and Io is able to, through these ions, is able to connect with the Jupiter magnetic field. And in that process, there's a mechanism where radio waves are emitted anywhere all the way up to maybe 40 megahertz. So at 20 megahertz, you should be able to hear them. And that's really cool. What do you hear? For example, there's a couple of types. Here's one. You better play, you sucker. Oh man, I tell you, I don't know why maybe I did it wrong. It says not found. I want to cuss so bad right now. I won't be able to let you hear those. Oh, here it goes like, okay, I can simulate it. All right, you got the picture. Right? Then you hear another one. The other one that emits is it's like popcorn. Okay, that's I get excited about that one. It can be fun. The SID, keeping an eye on that clock. I got to when? 10 up?
10 up.
Okay. Okay. The SID, I'll tell you what I'm going to do. I'm going to leave this PowerPoint with Mark so that you can pace yourself a little bit better on some of these things. I mentioned, and having mentioned what I mentioned, these pictures get a little bit more particular. They show you a little bit more of those details, but I've already hand waved some of them away, and I'm just showing you that it's not as expensive to do some of these things as you think. Like for example, here's the picture of on a quiet day.